Start this lecture by talking about quadratic equations and quadratic extensions in fields of characteristic not equal to 2. So this characteristic not equal to 2 assumption is really important. I'll say something about that below. All right, so here's the setup. Let's say that F is a field with characteristic of F not equal to 2. We're going to let K be an extension of F of degree 2. And we're going to take any element alpha that's in K, but not in F. So what do we know about alpha? Well, by proposition 12 that we proved last time, alpha satisfies the polynomial in F bracket X of degree at most 2. How do we know something about the polynomial satisfied by alpha? Well, it can't satisfy a polynomial in F bracket X of degree 1, because then it would satisfy a monic polynomial in F bracket X of degree 1, and it would have to look like X minus alpha. And this coefficient minus alpha is not in F. This polynomial can't be in F bracket X, because the one thing we know about alpha is that it's not in F. All right, so what is this polynomial satisfied by alpha? There's this unique monic irreducible polynomial of degree 2 that alpha satisfies. It's minimal polynomial over F. So M alpha F X has degree 2. So what does it look like? It's of the form x squared plus bx plus c for some b and c in F. All right, so first, how does the field generated by alpha over F relate to K? Alpha is in K, so certainly this field generated over F by alpha is a subfield of K. This field, by definition, contains F, and it's not equal to F because this one contains alpha and F does not. So what do we know? F adjoint alpha, this is a vector space of dimension 2 over F. We get it. We have gotten this field by adjoining an element whose minimal polynomial has degree 2. So that's the dimension of F adjoint alpha as a vector space over F. And we also know that K is a vector space over F of dimension 2 because we started with the assumption that K was an extension of F of degree 2, which is the dimension of K as a vector space over F. So if you have a vector space over a field of dimension 2, it only has one subfield of dimension 2 over that vector space, which is the whole vector space itself. So what does that mean? That means that the field generated over F by alpha, F adjoint alpha, must be equal to the whole field K. So what does this discussion tell us? If we start with a degree 2 extension of a field, then we can describe it as F adjoint alpha for any element alpha that's in K but not in F. So we can write it this way, but we can write it this way in many, many, many different ways. All right, so now let's talk about what we know about this minimal polynomial. Well, okay, what do we know about it is that alpha is a root of it. So how do you describe alpha in terms of these coefficients, b and c? This is going to lead to a higher level discussion of the quadratic formula that you have known since high school or middle school or whatever. All right, so usually what you say about how to prove the quadratic formula is by completing the square and then you like jump to the conclusion. So what does that actually mean? If you take x plus b over 2 and you square it, you get x squared plus bx plus b squared over 4. Okay, so we're in a field F. We're not in like the real numbers or the complex numbers. So it's worth saying one sentence about this. What is b over 2? We're taking b and multiplying by the inverse of the element 2 in the field F. So 2 better be a unit in this field F. Otherwise, this does not make any sense. And that is why it's so important that F be a field with characteristic not equal to 2. Because if F has characteristic 2, then 1 plus 1 equals 0. And writing b over 2, it's not even clear what that's supposed to mean. OK, so where does that leave us? X squared plus bx plus c is then equal to x plus b over 2 squared plus c minus b squared over 4. So what's a root of this polynomial? Well, it's something where this side is 0, which means that x plus b over 2 squared equals b squared over 4 minus c. And now, when does this happen? This happens if x plus b over 2 equals plus or minus the square root of the thing on the right-hand side, where what does the square root really mean? I'll come back and say something about that in a minute. And what is the square root? How do square roots work? I mean, this is the square root of the numerator over the square root of the denominator. This square root of the inverse of 4 is the inverse of 2. So this is plus or minus the square root of b squared minus 4ac divided by 2, or times 2 inverse. And OK, now just moving this to the other side, we get that x equals minus b over 2 plus minus square root of b squared minus 4c over 2. And OK, so putting this over a common denominator, this is the quadratic formula that you know and love from earlier in your mathematics education. Maybe you remember it with a song, for example. I'm not going to sing it here, but I'll pause and let somebody else do it.
X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a.
Great performance. OK, so I really do want to emphasize that this whole idea does require 2 to be a unit in F. So when F has characteristic 2, you have to do something else. I mean, it's still true that if you can take degree 2 extensions of a field that has characteristic 2, and you can still think about the minimal polynomial of an element that's in your extension but not in your original field F. But this part of the discussion needs to be modified. So I'll leave that to you as something to think about. There are lots of interesting things you could read here. All right, so now let's go back. I mean, what was the starting thing in this discussion where we had this polynomial? This is the minimal polynomial of this element alpha of k. So we know that alpha is one of the roots of this polynomial. So alpha equals minus b plus or minus the square root of b squared minus 4c over 2. And what do we know? Well, if b squared minus 4c was a square in F, then this square root would be an element in F. And then alpha would be minus b, some element of F, plus minus some other element of F, times 2 inverse, which is some element of F. And the whole thing would be in F. So we know that this b squared minus 4c is not a square in F because alpha is not in F by assumption. That's this whole thing that got this discussion started. This polynomial isn't just some random polynomial of degree 2. This is the minimal polynomial of an element of degree 2. So we know that this polynomial has to be irreducible. So this square root of b squared minus 4c really can't be in F. OK, so I'm going to pause and erase and just quickly say a little bit more about quadratic extensions in general. Let's continue our discussion of this degree 2 extension k of F. So we know that k equals F adjoint alpha, where alpha is some element of k that's not in F. Alpha has to satisfy some minimal polynomial of degree 2 with coefficients in F, x squared plus bx plus c. And the quadratic formula tells us that alpha is equal to negative b plus or minus the square root of b squared minus 4c over 2. So we just discussed the fact that b squared minus 4c is not a square in F because we know alpha is not in F. So let me just say something about this symbol, square root of b squared minus 4c. This denotes one of the two roots of the polynomial x squared minus b squared minus 4c in k. And what is this? This is something that when you square it, you get b squared minus 4c in k. So it's one of the two roots. There are two roots. There's this plus and minus here. The other one is negative of this. But there's no natural choice here for which of the two roots this corresponds to. These two roots are algebraically indistinguishable. This is different than what you might be used to from thinking about the real numbers. When we use a symbol like square root of 2 versus using negative square root of 2, we're not thinking of just square root of 2 being one of the two roots of the polynomial x squared minus 2 in the field R. We reserve this symbol square root of 2 to mean the positive one. But in this field K, we might not have a notion of what it means for one of these to be the positive one or the special one of these two roots. So this is worth thinking about a little bit, especially in contrast to how we use this symbol square root in the real numbers to denote the positive root. All right, so what do we know? We know that K equals the field generated by alpha over F. We're going to show that F adjoin alpha is F adjoin this element square root of b squared minus 4c, which is in K, but not in F. OK, so let's just show inclusion both ways. If you look at this formula for alpha, it's now clear that alpha is contained in the field generated by square root of b squared minus 4c over F. That if you're in a field that contains F and contains this element square root of b squared minus 4c, then you also contain this element alpha. OK, so it's clear that F adjoin alpha is contained in F adjoin the square root of b squared minus 4c. But what do we get this from? We solved for alpha in terms of this special element. We can just solve for this square root of b squared minus 4c in terms of alpha, multiply both sides by 2, add this b to both sides, and you see that square root of b squared minus 4c is minus plus 2 alpha plus b. So if you're in a field that contains F and also contains alpha, then you also certainly contain this element. So this field F adjoin square root of b squared minus 4c, there's no a, is contained in this F adjoin alpha. OK, so what are we seeing then is we started with K, just a degree 2 extension of F. And we took any element that was in K and not in F and saw that K was equal to the field generated by alpha over F. And then we saw that this field generated by alpha over F was the same as the field generated by this element square root of b squared minus 4c over F, where this b and c came from the minimal polynomial of alpha. So these elements have a special form. They're the square root of something in K that is not a square in K. So what we're seeing is that any extension K of F of degree 2 is of the form F adjoin square root of D, where D is an element of F that's not a square in F. And conversely, if you have an element D in F that's not a square in F, what does it mean, square root of D? Well, it means it's the root of the polynomial x squared minus D in K in some extension of F. So every extension of this form gives you a degree 2 extension of F. So what we're seeing is if we want to understand all of the degree 2 extensions of our given field F of characteristic not 2, they all look like the field generated by square root of D for some element D in F that's not a square in F, the field generated by that kind of element over F. OK, so these degree 2 extensions get a special name. Any degree 2 extension of F is called a quadratic extension of F. And we're seeing that all quadratic extensions over a field F of characteristic not equal to 2 have a particularly nice concrete form that we can describe. So we already did an example of this. Early on in our discussion of rings, we considered quadratic extensions of Q. These fields, Q adjoins square root of D, where D is a square-free integer. And what we're seeing is that, in fact, these are all of the quadratic extensions of the field Q. There's something to think about here, because here I said that D is a square-free integer. And here I'm saying that D is an element of your field F that's not a square in F. And being square-free is not the same as not being a square. So we just have to recall how we were able to restrict to the case of square-free integers. If you have a rational number d that is f squared times d prime, then we saw, if you just look at what the elements look like, that q adjoin the square root of d is q adjoin the square root of d prime. So you can take all of the square factors of your, if you take q adjoin the square root of a rational number, you can take all the square factors and forget about them. They don't change the field that you get. And why are you allowed to restrict to integers? Well, if you have q adjoin the square root of a rational number a over b, just using this fact here, if you take this rational number and multiply it by b squared, that's not going to change the field that you get. That'll go into this f term. So if you multiply a over b by b squared, you get a times b. So you can always think of the rational number that you're taking the square root of. You could get the same field by taking the square root of the integer that you get by multiplying by the denominator squared.